Hey, babe,
What?
did you finish editing that video for my lecture?
I edited it.
You edited it.
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 I edited it.
Okay, cool. Hey guys, this is my lovely wife.
Hey.
She did us a huge favor and she just edited all of this lecture. Oh, understatement of the year, right? I just want to warn you, this is not a permanent thing. It's like probably a one-time deal.
Yeah,
so
it took me all day.
don't expect my production value to go up on a regular basis like this. But for today, enjoy. Let's go! All right. Yeah, we're talking about Kirchhoff a little bit for like 3 seconds again today. So last week we covered series circuits and how series circuits, how we can calculate power, how we calculate resistance and all of that stuff. Can anyone guess what we're talking about this week? Parallel circuits. Yeah, absolutely. Welcome to parallel circuits. So what you're going to be able to do by the end of today is identify a parallel circuit, hopefully. Determine the voltage across each branch. We'll talk about what a branch is, how to apply Kirchhoff's law, determine the total parallel resistance, which we kind of touched on during that day where we had those worksheets all around the room, and then how to apply Ohm's law, how to use a parallel circuit as a current divider. We did it with a series circuit for the voltage divider. In a parallel circuit, the current changes, so we're going to learn how to use the current divider, and then how to determine power in a parallel circuit. Who can remind me how we calculate power in a series circuit? Come on, guys, it's an easy answer. Theo.
Total current multiplied by total voltage.
No, I mean sorry, that's my mistake. You are correct. The question was confusing. If you have a bunch of components with power in a circuit, how do you calculate the total power?
Power total equals sum P1.
Yeah, the sum of all of the powers. Exactly. Just add them all up. Yeah, it's pretty much the same thing for parallel circuits. So let's get into it. So this is a parallel circuit. You'll notice there are these little dots, which we sometimes call terminations. But in this context, we're talking about each one of these as the start of a branch. So you'll see here, a parallel circuit is defined by a circuit with the path having multiple branches. And the branch is where it'll split off into multiple paths. So over here we have voltage comes from here, and then it doesn't have one path like it does in a series, but here it splits up into two different streams, and that's why we have two different paths. You can see that with the current being drawn in, how it's going in different directions. And then if we have multiple branches, then we have different streams that it goes through. And one thing that's a little bit interesting is that you see all of these blue branches and all of these green branches. Because they're on one side, they're kind of considered like a common branch for all of them. So these are a few different ways that people can draw in resistors. So in the first example, that's probably what you guys are used to seeing, where you kind of have like a ladder shape, and it just is very neat and organized. Here we have two resistors on diagonals, making like this little triangle shape. It's still two branches, right? Because here we have one branch over here going this way and coming back, and they rejoin over here. On this one, it splits up here. It also splits up and continues going this way. Each branch has exactly one resistor in it, and they rejoin here to continue to join back up. Over here on the third example, we have the resistor. Right off the bat, it splits off into two pathways. Unlike this one resistor is horizontal and the other one's vertical, but it's the same because we have one resistor this way, one resistor on this branch. Over here we have three resistors creating three branches. One branch is there, one branch is there, one branch is there, and they all join back up there. Here it gets a little bit more intimidating. But again, if I made these all parallel with the bar on this middle one here that has like a downwards triangle and an upwards triangle and another one at the end, this could just as easily be vertical bars of resistors, and it would make a lot more sense. But now we're trying to open our mind into how it can look different, because when you're dealing with a circuit, sometimes you need to make unique shapes to form it into a circuit board or something like that. And so we have, it branches off here, it branches off here, branches off here, branches off here, branches off here, and they rejoin all in the bottom branch. It's the exact same thing. And the same is true for every single one of these circuits. There can be more than one current path, which is like where resistor 1, 2, 3, and 4 are. And all of them are kind of having this common point. All of these blue kind of have this common point. All of these green branches have that common point. So down here, the current kind of like rejoins from up here, but on each one of these individual branches, it has a separate current, all right? And then we're taking a look across how can we measure that voltage in a parallel circuit. Over here, there's a pictorial version, and on the right, it's more the schematic version where we have our meters around each of the resistors. And so that's kind of how we would measure them. And you'll notice that the voltage is always the same on every branch, as long as they have the same entry point here. So we haven't really gone into compound circuits formally, but if there was like a resistor before they branched up into all of these, that point where the branch starts to split off into different segments would be the total voltage that gets split between each of the branches, and all of the branches together would act as like one resistor in parallel with the other one that's in series with it. But that's just jumping ahead mentally. You don't have to know that for this class. So another interesting thing, just because I didn't really know this until I started to work with robotics and stuff like that. This pictorial version, if you ever get a request from a boss or something, and they ask you for a pictorial topology, this is basically what they're asking for. They want to see each component, what it looks like, not just like a schematic that has the symbols, if that makes any sense. Now, when it comes to calculating the current within a circuit, the way to think about it is what's going in gets split up into each of the branches. So if I know the current on branch 2 where resistor 2 is, and I know the current on branch 1 where resistor 1 is, and I added them up, it's going to give me the total resistance, because in this circuit there's only 2 resistors. So the other way to talk about it is all of the current in is equal to the current out for each of the branches that it goes to. Is that straightforward? Am I going too fast for you guys? All right. Everyone know, if you need me to slow down, I'll slow down. I had the best advice when I was younger. I was told it's never a student's fault if they don't understand something. Each student is like a combination lock, and it's the teacher's duty to learn the right combination for that student to succeed. So please, I really appreciate when you guys give me feedback, because ultimately I'm here to help you guys succeed. So if you guys can give me the path or the secret keys, like, it just makes my job easier. Okay? And I think you guys know I'm pretty cool when it comes to taking feedback. I'm not gonna scream at you. I'll probably just give you praise or something, because I know it can be scary sometimes. Okay, so in this circuit we have 2 resistors. Now we can throw in some currents to these to get like a more practical idea of how to do this. The first resistor has 5 milliamps going through it. The second one has 12 milliamps going through it. If we wanted to calculate the total current in the circuit, we're just adding them together. The first current plus the second current, which is going to be 5 milliamps plus 12 milliamps, which is 17 milliamps. We'll do a few more complicated ones. Another way to phrase this is the current total is minus the current of each of the branches. So current of resistor 1 minus current of resistor 2 minus current of resistor 3 minus current of n, right, resistor, you're going to end up with 0, right? Because what's going in is coming out. So for now, we're going to skip over to resistance. Is everyone okay with current so far?
Well, currents. Yeah. Okay.
We're also going to talk about current divider today, but just for adding and subtracting
We
them.
haven't already talked about that, right? That we're getting
We
to
have
it.
not talked about current divider yet. We've just talked about how to add current together to get the total current. Yeah? Jeremy, did you have a question? No? Okay. Just stretching? Cool. So now here's where parallel circuits have the ability to get a little bit confusing. And that's because we're talking about resistance now. So the easiest way to phrase it is if you were to take the resistance of each branch individually, the total resistance will be less than the lowest resistance. Take a second to let that sink in.
It's less than the total resistance.
Yeah. So I just want to make sure my phone doesn't accidentally go off.
How is that possible?
That's the question I wanted to hear. Absolutely. We're going to get into that in 2 seconds. So, how is it possible that the total resistance in a circuit is less than the resistor with the lowest resistance? Yeah, Theo.
Because it has multiple paths to take. So it can, you have, if it was just a 10 ohm resistor,
Mhm.
whenever they're in parallel, it's always lower than the lowest resistor, lowest ohm resistor. But if you were to just have the 10 ohm resistor, then would only be able to go through the 10 ohm resistor, that's 10 ohms. But now you've added 2 other paths, even if it has a higher resistance, it still has more flow than 10 ohms.
Yeah, that's a very interesting way to think about it. So
doesn't
yeah.
that mean that if you have, let's say, essentially a wire that shorts a circuit, and then you have a huge resistor, I don't know, like a huge resistor, there's still current going through the high resistance resistor, despite the wire basically shorting.
Yeah, I think what you're trying to say, and correct me if I'm wrong, the mind-boggling part is that if you were to have like 3 resistors like this in parallel, and I were to short the 10 ohm resistor, the total resistance in the circuit would go up.
It would go up. Wait, why
If
is it
I
going
if
up?
I shorted the 10 ohm resistor, because that's the one with the lowest resistance.
Sorry, okay, so short means like you bypass it.
I
right?
bypass the 10 ohm resistor, yeah.
And
The total resistance goes up.
that's crazy.
Right? But what makes it a little bit less crazy is we have constant voltage between each of these branches, right? And current likes to follow the path of least resistance. So we're going to learn fairly soon that most of the current is actually going to flow through the lowest resistance.
See, that's what I kind of understand, but
We'll get into it more, it'll make more sense, but I just want you guys to remember this because for me it was super anti-intuitive. And then the more you think about it, like it's just so mind-boggling. The lowest resistor is setting up the resistance of the entire circuit. It's unbelievable. So before we go back into resistance, we're going to talk about something called conductivity. Did I get that right? Yeah, conductance. Conductivity, conductance. How well does a material conduct electricity, right? So for conductance, in a parallel circuit, we just add them up. No problem. Total conductance is equal to conductance 1 plus conductance 2 plus conductance 3 plus conductance n, right? And conductance is measured in Siemens. Now resistance is measured in ohms. You can think about conductance in a way kind of like an anti-ohm, but whatever. Well, because what's ohms? Ohms is the measure of resistance. So if I'm saying how easy does it travel through the wire, it's like the opposite, right? Makes sense. So if I wanted to know the conversion between conductance and ohms, because we're thinking about them like anti each other, it's literally, quite literally, conductance is equal to 1 over resistance, or resistance is equal to 1 over conductance, aka they're inversely proportional. All right, so over here, if I wanted to know the total conductance of this circuit, just what's the conductance of resistor 1, resistor 2, resistor 3, all the way up to resistor N, and we'll get the total resistance. Now, over, are we going over it, sec? Okay, whatever. It's what I've been saying for like 10 minutes. So because we know that these are transversely proportional, let's talk about a few other things really quickly, and then we're going to finally get on with the whole how do we deal with resistance conversation. So remember we were talking about Ohm's law a couple weeks ago, and we were saying because it's V is equal to IR, that voltage is proportional to I, and voltage is proportional to R. And I, because if we wanted to separate I and R, we have to divide both sides by whichever one we're trying to move, is inversely proportional to resistance, aka resistance is also inversely proportional to current. So this is all gonna like just feed into this analogy on conductance versus current and resistance, and we could also apply it to voltage and all of the other things if we wanted to, except for the fact that voltage isn't changing here. Excuse me. So if we increase the conductance, that means the resistance is going to go down, right? Because these are inversely proportional. So if one goes up, the other goes down. The other one is going to be related to current. So what's the relationship between current and resistance? Well, these two are inversely proportional. So if this goes down while this one goes up, if we wanted to talk about current related to conductance, well, this is just going to do the opposite of what resistance is doing, right? So it'll go up at the same time. So if conductance goes up, then the current goes up, which makes a lot of sense because current likes to take the path of least resistance. And therefore, if we were to also, I think we're just saying the same thing over and over again at this point. So I'll just skip the rest of it. But that's the general idea. You can apply the logic to each one of those if you want to. Take your time. You have Ohm's law. You can break it down into which ones are inversely proportional or proportional to the others, like we did over here on this line over here. And you can just think about it. If this one's going up and it's proportional, the other one's going up. If this one's going down and it's inversely proportional, the other one's going up. And you can make all of the relationships you want. Just remember that in a parallel circuit, voltage is staying the same through different parallels. So there's really no point of throwing voltage into the comparison, because it's just, if we're purely talking about parallel circuits, it's the same. Yeah? Anyone confused by what we've talked about so far here? A little bit? What's the question?
I don't have any question. It's just like,
Where do you feel fuzzy?
it's mostly with like the.
Come on, bring it out, bring it out. There's no such thing as a stupid question, like actually.
No, I just
to that.
It's just like I don't know how to say the question.
Try to work through it with me, because I'm sure if you're feeling fuzzy about something, someone else is as well. And I really don't want anyone left behind. Pressure. Think out loud as best as you can. Where do you understand up to?
It's mostly like the last part, but yeah.
Okay, so G is conductance, right? Current is current, and then resistance is resistance, right? So what we were saying is, we know already from here, and you know how we were saying conductance is like the anti-resistance? So when conductance goes up, resistance is going down, because they're literally opposites. One measures how hard it is for the current to flow, one measures how well it flows. They're like literally opposites. That's their job. And then So we want to know between conductance and current, which honestly we're just trying to look at the different knobs and pedals and see how everything moves like all of the controls. When it comes to current, from Ohm's law, V is equal to IR, we see that I and R are like this, right? They're multiplied by each other and equal to voltage. So if we were to isolate for resistance versus voltage, if we want the relationship between current and resistance, we have to divide both sides by one or the other. Let's say we divide both sides by resistance. So then we'll have V over R is equal to I. And then you can see the relationship here between the two of them. So they're also inversely proportional, which is what these two are saying here, right? So when you have these two saying that they're inversely proportional because we know Ohm's law already and we trust Ohm's law, then we can say, okay, so then resistance is always going to move in the opposite direction of current. So if resistance is going down when conductance goes up, then when conductance goes up, current's going to go up. Yeah. Does that clarify what was bothering you? Okay, cool. Yeah, Andrew?
Could you kind of by proxy say that like resistance instead of electrons is flowing to the opposite side of the battery? And you could in turn use that resistance like Lars said, because that kind of dictates work.
Sorry, I'm not understanding the question. It's my fault. I'm trying to comprehend.
So-
Can you say it one more time?
Yeah, so you know how electrons, we know that electrons do work. And
Yeah.
in order for electrons to do work, some amount of resistance needs to interact with them, right?
Okay, yeah, you need some amount of resistance
Otherwise
for,
nothing happens.
or else it goes to infinity and melts everything. Yeah.
So actually it wouldn't even melt anything because it just keep conducting.
Well, then it has infinity. Sorry, if there's no motion, you have infinite resistance.
It's not a
Like a really high
situation that we
amount.
would realistically have.
I love these kind of questions because I'm the type who asks them. But
So can we get back on track, Will? Wow, look at me. So if we have electrons moving to the opposite side of the charged battery,
Okay.
we in theory have from the resistor
here, so we have a battery,
how do I
right? Positive, negative, and it's going. You're just saying it's going straight here.
no.
What's happening in between?
There's a resistor, let's say, in the center. Yeah.
Okay, so you have a resistor here.
So couldn't you treat the resistor as like the inverted battery, where
Could you
it pumps, let's say, ohms to the positive side of the terminal, and you could use that to find work, because it seems like it would give you the same result, just through a different perspective.
Well, it's what is valuable work, and these don't act as a pump, right? This is actually slowing down the current.
I know,
So-
and that's what I'm kind
Yeah.
of saying as a pump.
So so here's the deal. A pump increases the flow rate. If we were to bypass this, the flow rate goes to infinity. So it's like an anti-pump because it's literally slowing down the flow.
But it still manipulates the speed of electrons.
Yeah, for sure.
So-
In a way.
Doesn't that also mean it technically pumps just in one direction?
It's it's slowing it down. It's more like a dam that controls the output speed, or a throttle
I'll
valve.
look into it. I'll look into it.
Yeah, we might just be disagreeing on semantics, though. I'm not a huge fan of saying it's a pump, though, because for me, a pump is something that would like move. If we're going to compare it to a pump, we would be saying we're comparing it to water flow, right? Water flow would be the current. So if it's a pump, it's something that increases the speed of water flow. Which direction you decide to push that in is fine. The battery is more the pump. If we were going to use that analogy, just you gotta keep your analogy straight, you know.
Yeah.
Okay. Yeah, if you want, we can talk about it later. Okay, so I think we've talked a lot about this slide, so we can go ahead and move on. we talked about how if we were to add up all of the conductances, then we're going to have the total conductance, and then total conductance would be inversely proportional to, or literally inversely equal to, the total resistance. So the way we could do that is if we had the resistance of each resistor, we could add the inverse of resistor 1 plus the inverse of resistor 2 plus the inverse of resistor 3 all the way up to resistor n. And we can rewrite that by adding a -1 exponent to each of the resistors' resistances. And if you guys pull out your calculators, you should be able to find a button that should have like a -1 exponent to it, which will make your life super convenient when you're running calculations in parallel. So, do you guys remember when we had this whole conversation on the board? Do you want me to redo it? Because I feel like now it's probably a bit more applicable. So let's erase what we got here, and we'll talk about resistance this way as well. This is one of the core foundations for parallel circuits that you'll really need. So it's really good we understand this part really deeply. So the idea is 1 over, in parallel, for parallel circuits, 1 over the total resistance total, is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance n in the middle, which is the same thing as what we're seeing over here, because we said the conductance total is equal to 1 over R total, and then the conductance is equal to the sum of conductances. So the inverse is true for resistance. So we're literally just painting out this equation here through our understanding of conductance. Everyone okay so far? You a little bit lost? Okay, cool. So now we're saying if we wanted to make this a lot easier to deal with, because like imagine running this on your calculator. You'd have to first say, okay, what's 1 divided by the first resistance, and write that number down or save it in your calculator. What's 1 divided by the second resistance? Put that down. And if you have like 10 resistors, you're gonna be so miserable. Like it's gonna be like a nightmare to deal with. So we wanna make this more manageable. So what we can do is we can use inverse properties, right? So if I put anything to the exponent of -1, it's gonna flip the sides. Over the numerator will become the denominator will become the numerator. So we can do that for every single piece here. So we can say R total inverse is equal to resistor 1 inverse plus resistor 2 inverse, resistance 2 inverse, plus all the way to resistance n inverse, right? This is already like such a step up. Because now you just put in the resistance -1 on your calculator plus resistance -1 on your calculator plus all of the, you have 10 of them, it'll take you like 10 times. You get your total answer, you hit -1 again, it'll give you your answer for resistance total. Now, if we want to make that even prettier, we can just apply this to everything, right? So we can do R total is equal to, and we'll put everything in brackets, R1 plus R2 inverse plus all of the ones in the middle plus Rn inverse, and then another -1. I feel like they usually use square brackets for this. Isn't that gorgeous? Like you can just pop that in anywhere. You could have that in the middle of an equation where you're adding things together. You could say this resistance 2 is actually 2 resistors in series. So this resistor is actually going to be resistor 4 plus resistor 5 if you wanted to. Yeah, you can do so many things here. And then obviously that would have the -1, so the -1 would be like, if we were to zoom that out. You can do so many things with this format. It's unbelievable. So let's keep on moving and see where we end up. And on the slideshow, we just got back to here, which we talked about. And So now it's going to ask us to take a look at this schematic. Okay, this schematic is going to have 3 resistors in parallel. Each one of them has 300 ohms, and we want to know the total resistance for the entire circuit. Who can plug those in really quick? So let's say we're doing it this way. RT is going to be equal to 300 to the negative 1 plus 300 to the negative 1 plus 300 to the negative 1. Now you'll notice I haven't put in my ohms yet because I like to follow procedure, but I'm also lazy. So I'm going to just you know how you can factor units together or you can factor a number together? I'm just going to factor the unit ohms outside of the bracket so we know whatever's inside here is supposed to be in ohms. And then I only have to write it in once instead of 3 times.
Won't it get a little confusing when you write, for example, one is 300K and the one is 300?
Yeah, so in that scenario, it probably pays off to just leave them inside here. If this was kilo ohms and this was mega ohms and that was giga ohms or whatever the case is, for sure that's a better solution, and then you don't need to factor them out. But we're dealing with straight ohms for all of these. But really good point. Situational awareness is super important. So who can give me the answer for this?
Is it 100?
It's 100, yeah, 100%. It's 100 ohms. So I'm assuming you guys took the inverse of 300, technically just times 3, and then you took the inverse of that, and it gave you 100 on the dot. Now, is it not interesting that there's 300 ohms, 3 resistors, and the total resistance, and did I exactly a third of 300? It's pretty cool, right? Maybe you guys can start to see the trend. So here's the answer. This is what you guys did. Do you guys see this button? Were you able to find on your calculators the one that shows you the -1? How to inverse things just from your calculator? Most valuable button to find. Make sure you know where it is. Spend time on your homework at home right now, looking at your calculator. Find that button. Make sure you know how to use it, because you'll be very, very miserable. It also shows up as 1 over x sometimes. And yeah, you guys were right. It's 100 ohms. So now we have the situation that Arwin, right?
Yeah.
Yeah, Arwin was talking about. So we have one that's 4.6 kilo ohms, 7.5 kilo ohms, and 43.6 mega ohms. Who wants to run these numbers? Someone got one yet? Brackets are OP. Yep. 2,851. 2.85 kilo ohms. You got it. That's really accurate. Good job. Now, this is another thing to talk about. It's kind of a side note, but it's also super important. When you're in this class and in general when you're running calculations, your final answer should follow your significant digit rules. In this classroom for significant digits, we make your life simple. We just say, give us 2 decimal places. You're good to go. You don't have to think about it. But whenever you're running numbers, you want to keep as many exact numbers as you can while you're doing your calculations, and only your final answer should you put with a format of, in this case, 2 decimal places for significant digits. There was a note there I forgot to say. Yeah, that's pretty much the same thing. And if you don't get that exact value over there, you've done something wrong, but you guys are fine. You probably missed something or whatnot. Okay, so here we're just talking about format when you're writing. So up here you can see the answer is the same, but this is wrong and this is right. Who can spot the difference? I've lost so much time to this problem. Come on, you guys play the games where there's two pictures and you see something in one picture and it's not in the second picture. What do you guys see? Top and bottom. What's
There is no need for brackets. Power to the -1.
Exactly. There is zero need for brackets over here. This is the exact same as R1 inverse, with or without the brackets. It's completely unnecessary. You will spend a lot more time adding in brackets where they're just not necessary. So you can just pop in all of your numbers, throw the -1 on each of them. No need for all of the extra brackets. Literally, this is 6 extra button clicks that make confusion, that like when you're going through 10 or 20 resistances can really throw off your entire calculation. Imagine you finish typing into your calculator like 15 numbers and then you realize that you accidentally put a bracket where it's not supposed to be, or you miscounted the number of brackets, or you didn't close one and now it's giving you a syntax error on your calculator. Like, it's gonna eat up so much of your time. It's not worth it. Just know how to use your calculator, what's necessary and what's not. It's kind of like in the lab when I'm getting you guys to do your demos. And some people who will definitely remain nameless, and they are all getting better, will just kind of push everything, trying to figure out what works in front of me instead of trying to figure it out before I get there. And or when you're playing like one of those old-fashioned games like Mortal Kombat or something, and you just press all of the buttons randomly. Anyone here play like Mortal Kombat or Super Smash Bros. Or something? Come on, no one else has played one? Something similar, just the idea. It's a Capcom, anything, okay? Tell me, has there ever been a case where someone who knows what they're doing lost to a button masher? No, definitely not. Because if you know what you're doing, you get your timing down, you get your combos down, it's done, all right? It's capped, you know? So, same thing with your calculator. Know what you're doing, know what not to do. Same thing with your labs. Know what you're doing, know what not to do. And then everything runs super smoothly, and you save yourself so much effort and stress. Who's been a button masher before?
Everybody.
Has it not been stressful? Like, you're like, I hope this combo turns out. I want to do that really cool thing, but I have no idea what's happening, right? It's stressful. Save yourself. You do it once, right? I've been there so many times, man. It's like, especially in Smash Bros. Oh my
It
gosh.
doesn't even have to be in a game. Like I did something for one of my classes, right? And I had no idea how.
Yeah.
And it was. It's just
Yeah, repeating it is a nightmare.
Yeah.
But you know, it's funny because also sometimes just on the other side of the equation,
Because at least if you get it wrong, you know, like this is what you did wrong. It's your
Yeah.
side to do it. But if you get it right,
how did I do that?
yeah.
Yeah. Actually, you know, Thomas Edison had this really famous quote. Some of you might have heard it, some of you might not have heard it. But he said, "It took me 10,000 tries to make the light bulb. I don't consider those 10,000 failures. I just discovered 10,000 things that weren't a light bulb. And then I achieved my goal of making a light bulb." Both sides have their valor, but realistically, this classroom is about becoming super intentional. When you go into the workforce, you don't want to be guessing what you're trying to do. You want to have an inclination of what's going to happen, plan it, and then make slight trajectory changes when your ideals don't come out. Because if you're just shooting in the dark from day one, you're not getting there, especially as you work into more and more complicated systems. In the third year of this course, you guys are going to do something called a capstone project, which is literally, there's like over 20 pages of deep, detailed schematics down to every single wire, every single component, dimensions, everything down to the smallest details, the coding, what systems they're integrated with, how those systems operate, the manuals that go along with them. You know, like, it's a very, very intense project, and you have a total of like 4 months to design, 4 months to build, and you need every single minute. Can you imagine the difference between trying to do that as someone button mashing versus someone who's being intentional from day one? it's night and day. The people who button mash do not finish. And it actually has a fairly scary washout rate, because you need to be working hard. You need to be planning out your time for the whole capstone. Luckily, it's a third-year course, so generally you know all the skills by the time you get there. But it starts off here. If you're intentional from now and you work hard to keep your focus, you learn how to manage your time properly from here on out. By the time you get there, you just need to follow the behaviors that you've already learned. There was this other sentence, I forget, I think Warren Buffett said it, but I also think it's from Atomic Habits. It says, the strings of habit are too light to feel until they're too heavy to break.
Say that again.
The strings of habit are too light to feel until they're too heavy to break. And it's so true. You got something for me? Okay, cool. Okay, let's keep on moving. Yeah, so, don't use brackets if you don't need brackets, and blah, blah, blah. Now, there are two reasons why you would need brackets. The outer brackets, obviously here, because everything inside has to be added together before we get to that. Or, if, as Arwin was saying, if we have, like 6 kiloohms and 20 teraohms or whatever, if we have a bunch of different units with different metric prefixes, those go inside the brackets because we're going to swap those out with the 10 to the power of values. So you need those brackets to make sure that you're including all the numbers that go on the bottom. Yeah? And this is just more examples. Who can quickly give me the R total for the top question here when we're adding together 4.6 kiloohms? We have one resistor with 4.6 kiloohms, one with 7.5 kiloohms, and one with 43.7 teraohms. Half of you guys work on the first one, the other half of you work on the bottom one. I think they're the same question though. It's a really good opportunity to practice those calculator skills.
I got 2.85K.
2.58K?
85.
85K? That sounds about right, and it's lower than the lowest resistor. So let's see. We don't have the answer, and it's probably right, because it sounds like it's in the right ballpark. We have two resistors that are approximately in that level, which would be the 4.6 and the 7.5 kiloohms. The one that's 43.7 teraohms is not affecting our value. Let's be really honest. It's very minimal. Yeah, Arwen?
No, I was gonna. You already said it, but like for example, if it's a large value like that, we don't really have to worry about it.
You should put it in your calculator because it might account for like 0.01 realistically. You could probably run the two numbers, and if you're rounding, you're going to get the same value. But whenever you're dealing with with calculations, you want to do exact values because here's the analogy. Whenever someone's trying to go to space, sure, in a short distance, a small misalignment might not be a big deal. But if we're trying to go from here to Mars, if you're 0.0001 degrees off, you're going so far away from Mars, it's not even, you're in a different you're in a different space entirely. Not to mention all of like the different like orbits and stuff like that as well. So yeah, no, it always have in mind when you don't know what section you're going to be working in. And there are some areas that, it really won't make a difference, but there are some areas with like very, very sensitive equipment that small, minute differences can make all of the difference. And you need to know what you're working with. And then now we're going to go into the product over sum method. So if I wanted to calculate the total resistance, we can do it the way we were talking about. But let's say I have the total resistance, or I'm saying, you know, the total resistance is, sorry, my brain is doing a weird thing. I want to know the two resistances, but I already have the resistances of the resistors for the area I'm looking at. So what I can do is, let's say there's only two resistors in the parallel. I could multiply the two resistors values together and divide it by the sum of them. And we'll do an example in 2 seconds. I'm going to get you guys to calculate both ways, or I'll do it with you guys on the board. So here we have two resistors. One's 680 ohms, the other one's 330 ohms. And so what we're doing is we're just doing what we just said. We multiply the two of them together on the numerator. So we have 680 ohms times 330 ohms. And on the denominator, we add them together. So 680 ohms plus 330 ohms. And the answer is going to give us 220 ohms. Now, we just spent a whole bunch of time learning a different method. So for the sake of making sure this new method we're learning is effective, we should probably check that the other method gets us to the same answer. You guys all agree? So let's do it. All right, so where did I put that marker? Here. So here we have two resistors. So it's going to be RT is equal to 680 to the negative 1 plus 330 to the negative 1 ohms, and that's to the negative 1. Who can run those numbers for me in a calculator? Spoilers on the board?
Yeah.
Yeah, you got 222? What did it give you, 222.1? 18? Out of curiosity, if you do that method, do you get the exact same value? Or is it approximately the same?
Exactly the same.
Exactly the same. So that's your proof, practically speaking, that both methods will take you to the same place. And the way you decide which one you use is what information do you have available and what is the easiest route for you to take. You'll notice a lot that there are two types of people. There's one that just starts solving, and then there's a person that takes a look at the equation and all their information and consciously thinks, what is the easiest way for me to solve this problem? And I'm going to tell you, the one who thinks about it before they act end up having a much faster time solving the problem. I'll give you a really good, real life, very relatable experience that most people would have experienced in their life. You go to the grocery store and you're going in for something very specific. Let's say it's a jar of, no, not peanut butter. Someone here is allergic to peanut butter. Of jelly. So you're going for a jar of jam, right? Now there's one person who's just going to walk in and start looking around. And while they're looking around, they're going to be like, okay, where's the jelly? Where's the jelly? There's some fruits. There's that stuff. It doesn't seem like jelly would be there. Ooh, I see flour. Flour might have jelly nearby it. They finally find their way after a couple of minutes around the store to the place that they have the jelly, assuming that they don't know the supermarket already. And then there's the person who walks in and says, okay, I'm looking for jelly. And they notice at the top of the store, there's like these big hanging signs on top of each of the aisles. And they just stop. They look around. They see all of the produce on one side, and they see these signs. And on one of the signs, they see peanut butter, jelly, condiments. And they're like, that's where I'm going. And they just walk straight there. Be the guy who looks for the signs.
So you're basically saying be the person who finds the patterns.
Almost. Be the person who's observant. It takes a few moments.
Well, I feel like the first person was also observant. They were just doing it in another way.
Yes and no, but they're being blindly observant, if that makes sense. Because they're just letting the circumstance of whatever they pass by be the result of what comes into their sphere, right? They just start walking in one direction and they find their way around eventually. They obviously have to pay attention to their surroundings.
To that.
Okay, so don't subscribe.
Sorry.
Who finds the jelly first?
I don't know. I feel like it's not necessarily the latter. Because there's some situations where looking at the signs, like you might just randomly pop into the right aisle. Oh, there's the jelly. Here it is.
But you're leaving it to chance, and over 99 out of 100 times, the person who takes a look around will be there
But
first.
then again, it depends on how fast you can gather that information versus how fast you can actually comb through it.
It is never possible, like unless someone is very like sight impaired, and this is getting way too specific into the metaphor.
Well, you brought up the
I
analogy.
did bring up the analogy, but like it's a very easily relatable analogy. It's not about the fact of the specific circumstance. It's about the person who plans and takes a look at the information and tries to be intentional about the way that they get there is going to have an easier time with their results than someone who just haphazardly goes into things without understanding the environment. And sometimes, like in life, there's also much more serious consequences for not understanding the environment before stepping in. In any case, that's a side point. You can subscribe to whatever you want to. I'm just giving you, from what I've seen, what helps the most people get to the goal. So let's see and calculate the total current now. So for this circuit here, this is where we can have both approaches, okay? One you can just start solving, and you might get to the answer pretty quickly. The other one is, let's take a look at what we have, right? So what do we know about parallel circuits? We know the voltage is the same at every branch. We know the current is changing, so we can't just find the current in one spot like we did in a series circuit and have the total current. And we have resistance for each of these resistors. So our two options is really, we can calculate the total resistance and then use Ohm's law with the total voltage to calculate the total current. Another very valid option is we can use Ohm's law on each one of these, get the current for each resistor and add them together. That makes sense to all of you guys? Which one's gonna be more efficient if you practiced it over time? Anyone take a guess? Yeah?
I think the second one, because then you're gonna know the current for each of the resistors.
So if we're concerned about the current of each resistor, that absolutely makes sense. What I would say is which one takes fewer moves? Kind of think about like chess. Anyone here play chess? That is awesome. I've never seen a room with so many chess players, and that makes me super excited. In chess, time isn't dependent on the amount of time that it takes to have the game, because sometimes people think for a long time or a slow amount of time. Time starts to become a factor of how efficient your moves are, in a way. Obviously, there's strategy and everything involved, but you'll realize it will take me 2 moves to get to this side of the board, if you're trying to get here, whatever the case is. So your maneuvers become a factor of number of turns. So I want to look at this kind of like as a factor of how many calculations we have to run. So let's write them down on the board here a little bit. So in scenario 1, we said, and this is the one that we said we'll add up the resistors, use Ohm's law for each one of them. So we'll say one move is calculate Ohm's law R1, 2, we'll do the same for R2, 3, add, we're calculating the current, sorry, my bad. Current for R1, calculate the current for R2, add I1 plus I2 for total current equals IT, and then 4 would be to calculate, we have the total current, that's it. End of story right there. So now here's the second method we said. We said we can do the total resistance. Total resistance. So resistor 1 plus resistor 2 is negative, and 2, Ohm's law for total current. Now, I will add a caveat that when you're learning how to do this stuff, you will definitely spend more time. But once you get used to the thought processes, they go by so fast that you can automatically start to see which methods will take you where faster. And I used to do calculus in university for real engineering. I took this course myself. This is the one I actually passed. I did not finish university engineering. And so in calculus, there would be places where if you don't follow a certain pathway, you cannot get to the answer. You have to do things in a certain order, or else it's impossible to get to the final result. So it's not as extreme here. You're gonna get, in most scenarios, if you just start plugging and chugging everything, you'll get all of the answers. You'll be able to get to the right answer one way or the other. But in terms of efficiency, you can definitely see this method takes 2 calculations. This method takes 3. It's a small difference here, but getting used to the process of observing them can make a huge difference over a long period of time. And so let's see how they decide to cover it in this slide. So we're saying the total current is equal to the voltage source divided by the total resistance. I think that kind of tells us which method we're going through. And so voltage source is, current is equal to the voltage source divided by the total resistance shown in the breakup between resistor 1 and resistor 2 added in parallel. And that's going to give us 279 milliamps. Anyone want to verify that on their calculator? Yeah, it's coming up clean. Nice. And then we can check it using the other method. So the voltage resistor 1 divided by resistor 1 is going to be 10 volts over 100 ohms, which is 100 milliamps. And then 10 volts over 56 is 179 milliamps. You add them together, and you get 279 milliamps. Now, here's another cool thing. Which one takes up less space on your paper? Method 1 or method 2? 1, right? Yeah, because you're doing fewer things. You can compress it all together really nicely. And we broke it down into different, like a lot of steps on the board here, but you don't have to necessarily break it down in your equation that way. Usually, you take a look at what you have, what you're looking for, and what equations you know, and then you can work your way from there to combine all of them together so that you end up with like a beautiful equation like this that solves everything in one go. But realistically, what's going into this is the breakdown of these micro steps. Does that make sense to you guys? Anyone have questions before we continue moving? I think we have another example after this, if I remember properly. Everyone's good? Going once, going twice, 3 times. Sold to the highest bidder. All right. So now let's talk a little bit about fuses. Let's say you're designing an automobile and you need to calculate the size of the fuse so that your car, won't break on you electrically. We all know cars are getting more and more expensive to fix, and you pretty much need an engineering degree of electrical variety to work on cars nowadays. But we're going to overly simplify the problem. So here we're going to have 4 lights in parallel. Each headlight has a resistance of 4 ohms. Each tail light has a resistance of 10 ohms, and the battery, the voltage source, is going to be 12.6 volts. What is the current running at the fuse? Who wants to all of you guys grab your calculators, solve this, and then tell me what you guys say. And a quick trick for calculating fuse sizes. They don't make every fuse size. Like they don't make, like, say, 8.6 amps of a fuse. That doesn't exist, right? You need to get standardized sizes. So like 5 amps, 10 amps, 15, 20, 25, something that's commonly produced. You're allowed to go a little bit over, but you can't go way too far over. Yeah, you have an answer for us?
Not an answer, but a question to that. In the homework, if I remember, there was a question that was asking the fuse size.
Yeah.
It was something above 5, slightly above 5, and from there on, would it be okay to go to the next size, which maybe would be 10?
Yeah, I would say it's never a good idea to go lower.
Yeah.
I think 7.5 amp fuses might exist. I also think it came with a catalog of different fuses that are available. So use your best discretion, but usually you don't want to go under that number. Because if it goes under, the problem is it won't be effective at all. As soon as you turn on your device, it has a current that's higher than the fuse rating, it'll melt, be destroyed, and you're done. You have to replace your fuse every time you turn on the device, right?
Yeah, that'd be the
What did you get for us?
8.82 amps.
8.82 amps. So what size fuse would you choose for the fuse?
10 amp.
10 amp. I think that sounds really reasonable. Let's see what's going on. So I'm assuming this is what you did. We calculate the total resistance, which is 4 inverse, 4 inverse, 10 inverse, 10 inverse, and it gives us a total of 1.42 ohms approximately. And then voltage source over resistance total gives you that 8.82 that you told us. A 10 amp fuse is exactly the fuse to use. Really good job. Okay, now this is a little bit about notation. So whenever you guys are trying to write down how to add up the resistance of there's a shorthand and there's a longhand. So if you're gonna try to write the longhand, you're gonna go crazy at some point because you're writing inverse, 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 big brackets, inverse. You know what I'm saying? So the easy way to do it is just use these parallel symbols between all of the resistors that are in parallel with each other, and that's, you know what to do with that. Yeah.
So then, like, let's say if R2 and R3 were in series, would you have like R1/R2 plus R3?
So what I would do is I would rename R2 and R3 into R23, and then calculate R23 separately, and the R23 gets added in parallel. Yeah? Did I see another hand? No?
So would R23 be like a combination of R2 and R3?
Exactly.
What do you-
So let me draw out the situation that was described.
Like, how are you doing that?
So remind me your name.
Harsh.
Harsh, you're the one who asked?
Yeah.
Yeah. So what Harsh was saying is if we have, instead of R2 and R3 being on separate rungs, we have R1 here. We have R2, then we have R3 in series, right? And then we have R4, and then we have R5. And these all come back here. If we wanted the R total, instead of writing it out like that, what I would do is I would say R total is equal to R1 parallel R23 is parallel to R4 is parallel to R5. And then, excuse me, separately I would say R23 is equal to R2 plus R3. And then you can, when you're plugging everything in, you treat them differently. You would add those two into a bracket before you take the -1 of it. Yeah? Okay, cool. So that should be pretty straightforward. This is the notation. Here's an example where we have 3 resistors with 300 ohms each. Without doing any math, who can tell me the resistance total? 100 ohms. Yeah, you have a good memory. Because there's 3 of them, there's 3 paths, they all have equal resistance. So because they're all equal, the total resistance will be divided by the number of parts, the number of branches. There's 3 branches, so by 3. And because each branch has 300 ohms, 300 divided by 3 is 100. One advantage of a parallel circuit is when a branch opens, other branches are not affected because the voltage is the same in every parallel rung. The only difference is the total resistance may or may go up or down depending on which resistor is removed. And that will very directly affect the total current as well. But in terms of functionality, like let's say we're talking about lights, which is what we're talking about right now, all of the intensities of every light will stay the same. Where if the lights were in series, if we were to open a switch that turns off half our lights, we would double or half our brightness if the light could handle that variation in voltage. Everyone good with me so far? Okay. So you can kind of see here, just interesting to take a look at. It's always really cool to look at these slides in more detail and just kind of like think about how they work. So over here we have the battery, and what's the first thing? Over here is a brake light that's actuated when someone pushes their brake. There's like a little normally open push button, and the first switch, the light switch, is separated from here. So you have the left and right brakes lights, and so these are always on because who wants their brakes to not work? They should always be operational, right? So there's no option to turn off the brake light. But then you do have a light switch. That first light switch, when it's enabled, turns on the tail lights and the low beam headlights. So all the way up to there, these two branches are connected before the same what's the word? The same common branch, basically. So yeah, these two over here, between the two switches, right? So when you close this one can be open, this one can be closed, but these two turn on and off at the same time. And when you have your taillights on, you want your low beam headlights on. And then the only other one that turns on is your high beams. Your high beams you can also separately turn on, and they only add in addition to the low beam lights. So you can kind of see how the logic here kind of progresses through the circuit, and at every single branch there's an individual fuse because each branch has a certain amount of current that's supposed to be running through it. So for the first branch here, for the brake lights, you have your first fuse. For the second branch here, for the tail lights, you have your second fuse. And then they use one for all of the low beam and high beam lights because they're going to be run at the same time, basically. So if that fuse blows, you want to make sure that it's the components are still safe, which is why you put a fuse in. Okay, so that's just like an interesting thing. Take the time sometimes to go through these and just break them down. Take a look at it, and then the same thing is true in your house. So we have the 110 voltage over here in your home, and then we have your breaker box, and from your breaker you have the lights in parallel. Each one of these lights have the switch individually associated to each individual light bulb, and then your outlets are also put in parallel because voltage remains the same. So as long as there's enough current to draw, it'll just pull the current for each device as more devices get plugged in until you reach the breaking point of that breaker. Excuse me. So now we're going to talk a little bit about current dividers. So we're getting into current dividers finally. So this branch goes into two directions. And so remember how we were talking about voltage dividers? So let's do a quick refresher on voltage dividers. And one of the reasons I want to do it with you guys this way before we pop it up on the screen is because I want you guys to have a good memory and a way to rederive it if you ever forget it. So for voltage, we know V is equal to IR. So if we wanted to look at the relationship between voltage and resistance, we know that voltage is proportional to resistance. So what we were doing is we were saying V source over resistance source is equal to, or resistance total is equal to Vx over resistance x, right? And then we apply this to that side. We multiply both sides by resistance total. So VS is equal to, or we're looking at X, right? Usually you want to know you could go either way, but usually you're looking for the specific voltage. So Vx is equal to Vs times, so Vx comes this way, so we multiply both sides by Rx, and divide both sides, this by RT, sorry. So what we did is we divided both sides by multiplied both sides by Rx. So if we do that in green here, Rx and Rx, these cancel out to 1, and we have this, and we just rearrange it so that we end up with it nice and clean on that side. And that was our voltage divider formula. Now here, and this is again only for series, because it doesn't matter in parallel, they're all the same. So for parallel, we have the current divider. Now, if we're looking for the relationship between current and resistance, so we're going to pull up the V is equal to IR again. And because I and R are next to each other, we have to divide both sides by one of them. So let's just do R because why not? And so we can see here, I is inversely proportional to R. So the same logic has to be modified a little bit for this to translate into a voltage divider, sorry, a current divider formula. So if we have I source, then I source is going to have to be multiplied by the R source, R total, which is going to be equal to IX RX. All right, and the reason for that is because they're on the same side, right? So I'm showing you they're inversely proportional. So when we flip it all around, it's gonna be different. So here they were top and bottom. Here they're on the same side, right? Because if we were to put over here as well, so V is equal to IR. If we were to make I equal to V over R, we'll see that these two end up vertical from each other when they're on the same side of the equation. So that's basically what we're doing. And if we wanted to really demonstrate how this formula comes into being, we could say, okay, well, here we know the current is supposed to be equal for whatever we're comparing on this. So in a series circuit, which is where this comes from, current is the same everywhere in the series circuit, right? So S is equal to I1 is equal to I2 ... IX, right? So we're just trying to say IS is equal to IX, and we're going to plug this in for both of them. So VS over RT, which is the source one, is equal to, this is just straight substitution, Vx over Rx. And we have that formula there. Does that make sense? Is that like really step by step how we got there? So we're going to do the same thing now for current, just to like really knock into our heads how we got here. So over here we're saying voltage is equal to IR. We know voltage is the same everywhere in the parallel circuit on every branch. So if we have voltage source is equal to voltage X, and we're just subbing into that IR, right? So I source times RT is going to be equal to IX times RX. That's just a straight substitution and a straight substitution, and we're over there. Does that make sense? You guys following me? Really step by step, straight from Ohm's law? Okay, cool. So from here, if we wanted to know, do you guys want to do it for IX or do you want to do it for RX? IX? Okay, so let's do that. So we would divide both sides by RX. And these will come to 1. So IX is equal to IS RT over RX. And I think that's what we're going to end up with in 2 seconds when we get there. And you'll notice that this one ends up on the bottom because they're transversely proportional. Yeah? So let's go and take a look at how we describe it here. So it's basically talking about what I was just talking about, but in more words and hopefully logic. If we have two parallel elements of the equal value, then the current will divide equally. So back to our previous slide over here. If we had two segments and 200 ohms on each of them, then like it divides equally if it's the same resistance in each branch. So if we had two branches, 200, what's the total resistance? Two branches, and each branch has a resistor with 200 ohms. It's also 100, exactly, because it gets divided equally. Yeah. So, and for parallel elements with different values, the smaller resistance, and the one with the smaller resistance is going to have the greater share of the input current, which, in a more practical manner, means, let's draw this out over here. You guys are good if I erase this? So if we have a circuit with two resistors, right? And one of these resistors is like 200 ohms, and this resistor is 100 ohms. Which one's going to have more current?
100.
Because current likes to follow the path of least resistance. Exactly. So current is going to be greater, current is going to be lower, because they're inversely proportional. So that's what that's saying. For the elements with different values, the smaller resistance has the greater amount of current that's going to run through it. And for a parallel with two different values, the current will split with a ratio of the inverse of their resistor values. That's a whole mouthful, right? So if I were to take both of these together and just add them up to a total number, right? It's going to give me like 300, right? I like to think about like 300 parts. And then I can simplify all of these. So that we can kind of look at this as, because we're just looking at the ratios for now. So this is a 3, this is a 2, and this is a 1. But it's going to be inverse. So these two are going to trade their values. This one's going to take the one that's 2 times the current, and this one's going to take the one that's one part the current. If that makes does that make sense to what I'm trying to say? So this one's going to end up with 1/3 current. This one's going to end up with 2/3 current. It's just, you guys get what I'm saying. We looked at the total parts. From that, this has 200 parts, but because more current goes to the one with less resistance, we swap which one has which part. Yeah? So here's the example. The total current is 300 milliamps, and the first resistor here has 100 ohms. This resistor has 200 ohms on the bottom branch. And so when we split it up, the one that has the 200 ohms gets 1/3. So that's going to be the 100 milliamps going down that one, right? 1/3 of 300 is 100 milliamps, and the one that's 100 ohms is going to get 2/3 of the total current, which is the 200 milliamps over there. Am I still making sense? Okay, good, because my brain's starting to collapse, and I want to make sure we at least get to the end of this. So what do you think the currents through these resistors are? I feel like the answer's already there.
Hello, everybody. So I'm popping this question back up on the board because when we were in class, I was getting a little bit confused on the concept I wanted to show to you guys, which was related to the idea that, if, let's say we talk about money instead of resistance and current, if you were paying 60% for an object, or sorry, if it was 60% off, you could transversely do 100 minus 60 to get you your 40% that you're paying. And just how you could relate that into the same terms as calculating the current from resistances. Now, my big problem, which I realized after class, is that the relationship between resistance and current is inverse. So current is equal to, sorry, not equal to, proportional to 1 over R. And that makes a huge world of difference in terms of how we're going to calculate this. So over here, we're going to treat, just for the ratio part of this, the current as 10, and then for each of these resistances, for we're basically dividing everything by 100. So this will be 1, this will be 2, 3 will be 3, and 4 will be 4. And then we can start taking the inverse of each of these. So 1 inverse is going to be 1 over 1, which is still 1. And then 2 inverse is going to be 1 over 2. And then 3 inverse will be 1 over 3. And you know what? I guess for simplicity, we could even, whatever. We did 4, let's do 4. And 4 would be 1 over 4. I just know that this number is going to be it's like 0.333, which is less pretty to deal with, but we'll deal with it. All right, and then we'll add up all of these. So if we take the values for these, this is 0.5 and 0.333 and 0.25. And what we're going to do is we're going to add all of them up. So instead of adding up the 1 plus the 2 plus the 3 plus the 4, we have to add up their inverses. And this is also related to, conductivity being proportional to 1 over resistance as well. And then this one would be the part that is on par or on the same side of the equation as current. But I digress. So in any case, if we do some math over here, we're going to get, let me pull out a calculator real quick, 1 plus 0.5 plus 0.333 plus 0.25. That's going to give us 2.083. All right, so that's going to be our total. And then for calculating the ratio for each of them, it's just a matter of using the proportions out of this amount. So we'll start off with the inverse of 1. So 1 over 2.083 is equal to, pulling my calculator out again, clear 1 divided by 2.083. That's going to be approximately 0.48. So 0.48. And then we're going to multiply that times our 1,000 milliamps, because that's our percentage now, equals, and then we'll just do the same for each of these. And 0.5 over 2.083 is equal to 0.5 divided by 2.083. It's approximately 0.24, 0.24. Then we have 0.333 next, so 0.333 over 2.083. Popping that in the calculator. It's 0.333 divided by 2.083. It's going to give us about 0.16. And then we got our 0.25, 0.25 over 2.083. So again, 0.25 divided by 2.083. And that's going to give us about 0.12, which is going to be approximately 0.12. You'll notice now that like 0.48 plus 0.12 is going to give us our 0.6, and then our 0.24 plus our 0.16 gives us 0.4, so 6 plus 0.4 is going to be our full 1. So now we've gone ahead and got it out of 100 kind of thing. So this is the percentage. And then we multiply it by 1,000 times 1,000 milliamps times 1,000 milliamps times 1,000 milliamps, and our totals are going to be 0.48 times 1,000 is going to be 480 milliamps. 0.24 times 1,000 milliamps will be 240 milliamps. 0.16 times 1,000 milliamps will be 160 milliamps. And 0.12 times 1,000 milliamps will be 120 milliamps. Same story, all of these together do equal up our 1,000 milliamps. And this is an alternative way to solve, but this isn't the way you should be solving. This is just the proof of the idea to show you how they're inversely proportional. In terms of practicality, just add them up or use the current divider formulas practically. 40 milliamps, and then we have our 160 milliamps and our 120 milliamps. Hope this is helpful, and I will see you guys next time.
Okay, so this is back to what we were talking about before with the current divider. So you guys can see here, this is the inverse relationship between I and R. So this is where we just recreated the formula. We put them next to each other. So if we were to multiply both sides by the other one, we would have Ix times Rx on one side and RT times IT on the other side. And so that's going to give us our formula here. We went over how to derive this already, and then you could use this to calculate R1 and I1 and I2 using that same methodology. I don't think the answers are here, so why don't you guys take the moment to calculate this, and I think we're pretty much going to be done. We're going to have to skip over the last question because I think we're at the end of our time. Yeah, we need to get into our lab class. So quickly do this calculation using voltage divider, the one that's over here. If you guys need it, I'll write on the board again really quickly. And then we'll pretty much call it. So Ix is equal to IT brackets RT over Rx. Okay. Tell me as soon as you guys have an answer. All right, let's do it together then, just for time's sake. So we're saying IT over here is 300 milliamps. 300 milliamps. And it's multiplied by what's RT? So RT is going to be resistor 1 parallel resistor 2, all divided by, if we're just looking for R1, R1. And so that's going to be 300 milliamps multiplied by, it's 100 and 200 ohms. So 100 inverse plus 200 inverse divided by, and then R1 is 100 ohms. All right. Who can pop that in and give me a number? 200? 200 sounds like it makes sense because R1 should be 200 milliamps and R2 should be 100 milliamps. And if we go through, that is exactly what it shows us. And then this is just a more complicated version. There's a third component now, and you have to deal with power. The thing that we were going to talk about, we kind of like brushed over it at the beginning of the class. And please take the time. We're already over our time, so I'm rushing through the end of this. For this one, please take the time to go over it yourself. Try it and then compare the answer. It gives you a step-by-step breakdown of how to do it. And then for power, the total power is just the sum of all of the powers in the formula, in the circuit. And so this is an example with that, where you start to have to use power to figure out the answer as well. I wish we had more time to go over this, but we really don't. So please take the time to review. And then lastly, yeah, this is pretty much the same story here. Find the total resistance in the current, take the total current, take the current through each branch, the voltage across each resistor, and the total power in the circuit. Open branches. This is one more thing that's important to know. So over here, we were kind of going over it as an idea, but if I were to open this switch, resistor 1 will drop off, and the entire resistance in the circuit is going to increase because if we have two resistors, it divides the total resistance basically by 2. So if we remove one of those resistors, the resistance goes up in the total circuit. And yeah, just go through the rest of this and you have the summary. I'll see you guys downstairs.
Sir, I have a question.
Absolutely.